All right, so for today we are going to talk a lot about free body diagrams, and you might remember free body diagrams from last year. There are 5 free body diagrams that we are going to be talking about in class, 5 main types of free body diagrams. The first one is just like a tabletop, or maybe you consider this on the floor. It may or may not have friction associated with it. The next one is kind of like your inclined plane. This might be an example of somebody going up a hill or going up a ramp. The next one we can talk about are over the edge problems. These over the edge problems, and actually let's give a small diagram for each of these. So first you just have an object that's maybe on a surface, then maybe you have a ramp, you have an object going up a ramp of some sort. Over the edge problems were going to be your problems where maybe you've got an object that's connected to a pulley, and that pulley is pulling it, has a weight connected to it, and is pulling this object down and in this direction. Next example would be like sled or wagon problems. And for our sled and wagon problems, what we're going to see is an object that is pulled. Oops, give me 1 second here. An object that is pulled at an angle. And this angle right here is going to result in this object being pulled upward, but then also along a surface. And then our final one is going to be our Atwood machines. So in this scenario, I've got a pulley. Let's write Atwood. In this scenario, I've got a pulley connecting 2 masses. And we will see that one object maybe is going to be pulling the other object up and around that pulley. So with all 5 of these examples, we can find various different types of values. We can find the masses of our objects in a variety of these scenarios. We can find the acceleration of these objects. In the examples with the over the edge, we can find tension. We can find the tension of the string in a wagon problem. We can find the tension of a string in an Atwood problem. We can also talk about friction and what these different friction values will be. All right, let's get a new slide. Let's do a few quick reminders before we go anywhere. Let's remind ourselves that on just any box, we're going to see first the force of gravity. Now, force of gravity can be written a few different ways. We can write it F of G. We can also write it just as a capital W for weight. Sometimes you might even see it as a lowercase w. Even at one point, I've seen it as F of E for the force of the earth. In all those scenarios, you're talking about the exact same thing. You're talking about the mass multiplied by the acceleration due to gravity. Sometimes this is also written as mass times g. Remember that g and a are both the same thing, and as long as you're on Earth, we're talking about 9.8 meters per second squared. Now we find that there is going to be a partner force with our weight, and that is our normal force. And our normal force can be written a couple different ways. I've seen it as F of N, or I've just seen it as capital N. Your textbook uses capital N, but just keep both of those forces in mind. And now as long as this object isn't actually traveling through the table and has like an is at equilibrium, the normal is going to be equal to the weight. All right, let's give another example, however. Let's say that I have a table and I have a box sitting on a table, but then I'm applying a force to that box. So here is my awesomely drawn hand applying a force to this box. Well, this box by itself will have a weight value, and then this box will also have a force applied by me. We're just going to call that F. The normal force, again, as long as this box isn't actually traveling through the table itself, the normal force is going to be equal to this value right here and this value. So it's going to be equal to the weight plus the force applied. So that value is going to be larger. Now, I do want to remind you that forces are vector quantities. Forces are vector quantities, which means that magnitude and direction matter. The other thing about forces is when we draw a free body diagram, the size of the arrow, or really the length of the arrow, is going to be kind of representative of the force. And so a short arrow means a small force, a longer arrow means a larger force. If I'm comparing two arrows, I see that maybe the larger force is represented with a larger arrow. So keep that in mind as well. Next, let's talk about friction. Friction is the other thing I want to talk about before we begin doing any diagrams. So for friction, there's really going to be two different types of friction. There's going to be static friction, and there's also going to be kinetic friction. What we're going to see is that when we have static friction, our object is not moving. But when we have kinetic friction, our object is moving. For our static friction, our textbook gives us our F sub S. For our kinetic friction, we have an F sub K. These also are sometimes written as just F of F sub K, and then F of F sub S. Really, either one works for us. It doesn't really matter which one you choose. This brings us to our equation for really solving for the friction values, because that'll be important. Our equation for our static friction is going to be the static friction maximum value will be equal to the coefficient of friction in the static scenario multiplied by the normal force. Now, let's remind ourselves what that mu means right here. And let me get my highlighter out. Highlighter. Let's remind ourselves what this mu value means right there. The mu stands for the coefficient of friction. Coefficient of friction. And this value will often be given to you. And what this really is it's the amount of friction or the coefficient of friction that's unique to every type of surface we're talking about. And usually that's a supplied value. There may be situations where you need to solve for the coefficient of friction, but in that situation you'll be given the normal and you'll be given avenues to solve for the normal and for the force of friction in the static scenario. Now again, static means that it's not moving. So really, when we talk about a maximum value here, this is the maximum the friction can be without motion taking place. So really, the static friction can be less than or equal to this coefficient of friction multiplied by the normal value. It can be less than that because in all those scenarios, it's not moving. Let's jump over to kinetic friction side, and let's give ourselves a little barrier here for our notes. Let's get a new color. In this situation, the kinetic friction is equal to the coefficient of friction when our object is in motion multiplied by our normal value. Now you may be asking yourself, what is the difference between the coefficient of friction and the static value versus the kinetic value? Well, I'm glad you asked. Let's flip to another slide. Our coefficient in the static versus our coefficient in the kinetic. What we're going to see is that our coefficient of friction for the static is always going to be larger than our coefficient of our friction when the object is in motion. Always larger. And the reason why is because it takes more force. And the reason why is because it takes more force to set an object into motion than it does to maintain the motion. So what we're going to see is that it's really going to require more force to take a non-moving object and begin its motion. And that's why this value is always larger, because it takes more force really to overcome that static friction. But once we have set our object into motion, it requires less force to maintain or to keep that motion going. Hence why this value for our kinetic friction will be lower. All right, so we've got 5 free body diagrams to go through. 5 free body diagrams. Let's go to our very first example. Let's talk about an object that is sitting on a table. So our first example are going to be tabletop examples. Tabletop examples. These are also just like on the floor examples, or however you want to call them, basic horizontal examples. It doesn't really matter. Now the first force that we identify acting on this object, and let's get some information about this object first. Let's say it has a mass of 50 kilograms. Let's also say that we have no friction in this problem. Let's say this is a frictionless environment. So we have no friction in this first example. And let's say that the force applied is equal to 20 newtons. Now, last year, you might have written force applied with a small a right there next is a subnote to your F. You can write it either way. I think our textbook just writes F when we're only talking about one force applied. So it's up to you how you'd like to write that. So first of all, we're going to identify a couple of the staple forces that are going to be acting on our object. And I think that's going to give me an arrow. Perfect. So first we have our force of gravity, which is also known as our weight, our F of G, or commonly written as that. And whatever size this arrow is, that's going to be equal on the other side for our force normal, which we'll just write as normal. And we can calculate these two values right off the bat without really having to worry about anything else. Remember that our weight is going to be equal to our mass times our gravity. So our weight is going to be equal to 50 multiplied by 9.8. And that gives us a weight value of, I didn't calculate that on my paper. That gives us a weight value of 490 newtons. Now, these values aren't super important to us right now, mainly because the weight and the normal are going to be equal to one another, so they're going to cancel out. So these forces are balanced, they're in equilibrium, they're not really influencing the problem in any way. Now there is a force, however, that's being applied. We said that we had a force of 20 newtons being applied, and we didn't specify a direction, so we are going to just pick a direction for fun, and we are going to say that that is going to the left. There's our force applied. Let's label that force applied, 20 newtons. Now this is a frictionless environment. There's no friction in this problem. So all we have right now is the force applied. Well, let's say I asked you to tell me what the acceleration was. First thing you need to do is you need to find what the sum of the forces are in the x direction, because that's the direction that the motion is going right now. Now you've seen the sum of the forces in the x and sum of the forces in the y. What we're talking about is the horizontal, let me get my highlighter out again. What we're talking about is the horizontal forces versus the vertical forces. Now let's think about this for just a second. Our vertical forces are what? Balanced? Yes? Definitely. We see that our vertical forces are going to be, some of our vertical forces are going to be our weight minus our normal. Or you could do your normal minus your weight, depending on which direction you decide is positive and negative. Remember, force is a vector quantity, so these values are going to cancel one another out, and we are going to see that our force in the vertical is at equilibrium. Our force, however, in the horizontal is not at equilibrium because this object is in motion. We see that our force on the x is equal to our force applied. Well, that's really easy because we only have this one force acting on it. So now I can solve for acceleration by going Fa equals mass times acceleration. Well, I know what my mass is. I know what my force is. The force is 20 newtons. Is equal to the mass, which is 50 kilograms, multiplied by the acceleration a. Divide those out, I get an acceleration value of 0.4 meters per second squared. So this is your first one. These are tabletop questions in which there is no force or no friction involved in the entire problem, and that's how we could solve for something like acceleration. Let's do a problem in which there is friction. Let's grab ourselves a new slide. So now the example you see in front of you is going to be an example where we have an object sitting on the table or sitting on the floor, but there is friction involved. And let's get some general information about this one right away. Let's say that the mass is again equal to 50 kilograms. Let's say that the force of friction, let's do our coefficient of friction for an object in motion. Let's make that 0.09. And let's say that our force applied is equal to 200 newtons. Now, the next thing we need to do is just kind of identify some of the variables and begin drawing our free body diagram. So we'll get our arrow, let's get a color just for fun. There is our weight. In the opposite direction will be our normal. We can find our weight and our normal value by taking 500 multiplied by 9.8 to give us 490 newtons. Let's have our force applied be to the left again, just for fun. Let's give it a new color. Force applied to the left. And then this time it says we have a force of friction. Well, we're not quite sure what that value is, and let's label this F of A. For our force of friction, we're not quite sure what that value is because we need to actually calculate it, but we know it's going to be in the opposite direction. So we're going to say that F of K, because this object is moving, it is kinetic friction. Now, we can solve for a variety of things right away, but let's solve for the force of friction first. So our force of friction and the K value for kinetic is going to be equal to our coefficient of friction multiplied by our normal. Let's get a different color here. Let's scroll down just a tiny bit. What we can find is F of K is equal to 0.09 multiplied by 490. That gives us a frictional force value of 63.7 newtons. So now, if I wanted to still find the acceleration of an object in this example, what I would have to consider is, we remember from last time that our force in the y is going to be equal to 0 because our weight and our normal are going to balance one another out. But our sum of the forces in the x are going to be equal to the force applied minus the force of friction. And so what we can do next is we can actually solve for that total force. So let's scroll down just a little bit. We're focused down here. The sum of my forces is going to be equal to my force applied, which is 200, minus 63.7. The sum of my forces then will be equal to 136.3 newtons. Now, based on having this value for the sum of my forces in the x direction, I can go F equals ma, Newton's second law, and solve for the acceleration of this block. So F equals ma, that's why we love Newton and his second law. 136.3 is equal to 50 multiplied by a. Divide that out. The acceleration of this block is equal to 2.73 meters per second squared. Next, what we're going to do is we're going to look at sled and wagon examples. Now, sled and wagon examples are going to require us to do a little bit of right angle trig. So let's get ourselves a new slide. I'm going to pause this. I'm going to draw some stuff up here, and then I'll come back. All right, so let's look at a sled style problem. And really, this is just a box being pulled at an angle. So you don't have to call it a sled or a wagon. Well, we're just calling that to make it a little more interesting. In this example, let's say that there's a force applied by the pulling of this rope right here. And we can refer to that as the tension. And in our book, we just refer to tension as a capital T. And let's say that the tension is equal to 150 newtons. Let's get some other general information about this box. Let's say its mass is equal to 20 kilograms. Let's say that we do have some friction on the ground and that our coefficient of kinetic friction is going to be equal to 1, 4. Let's say that the angle with which this box is being pulled is going to be 10 degrees. Now, I know some of you are saying, boy, that does not look like 10 degrees, and I'm glad you are forgiving me for my not pretty drawings. Now, the next thing we can do is we can actually draw some of the forces that we're going to see acting on this object. Before we do any math, we can just draw these forces in. We have our weight down here. We have our normal up here. Notice that I'm drawing my normal strategically slightly smaller than my weight value. I'll tell you what that's all about in a second. We are being pulled at this value right here, so that's why we've got an arrow there, and we're going to have a small amount of friction in the opposite direction. Let's give these actual labels now that we just drew a bunch of arrows. So we've got weight, we've got normal. This is the force applied, but because it's a rope, we can say it's the tension. Let's say it wasn't a rope and maybe it was something like a hard handle to a wagon, then it could be force applied. They mean the same thing. And then this will be our kinetic friction. So the first thing I would do is I would find the x and the y components for my force applied or for my tension. So this will be force or tension in the x. This will be force or tension in the y. And now we've got to do a little right angle trig, and there's no shame to your game if you got to write SOHCAHTOA every single time you do one of these. You can do it. It's okay. I know not everybody needs that, but that is just fine. And we're going to see that the force applied in the x is going to be equal to cosine of our angle, which is 10 degrees, multiplied by our hypotenuse, which is 150. So that means our force in the x value is equal to 147.7 newtons. Now let's find our force in the y. That's going to be equal to sine 10 multiplied by 150. And what we see that is that value is going to be equal to, let's put that in a different spot. Hold on. That value in the f of y is going to be equal to 26.05 newtons. So now I have my x and y components for my force. And these are really going to be influential in what we see happening next. Let's talk about the sum of our forces in the x and in the y components. So the sum of our forces in the x and y component, and I'm going to have to move up just a little bit here. So the sum of my forces in the x component are really going to be the f of x, the force applied in the x value, which is going to be right here. But then also we're going to subtract our kinetic friction that we calculate over here. Now our force of values, or our sum of our forces in the y are going to be equal to our weight minus our normal. Ooh, but there's one more force that's playing a key component in our y value or in our vertical forces right now. Do you know what it is? Oh, it's our force applied in the vertical direction. We get that value up here. So now we can go through and we can kind of begin to solve some of these things. The one value we don't currently have is going to be our normal. We'll talk about that in just a second. And actually, let's talk about it right now. So let's find our normal value first. And just out of cleanliness and the desire to not compress things too much on this slide, I'm going to go to a new slide. But hopefully that does not mean you need to go to a new page in your notes. I just need to go to a new slide and we'll reference back and forth a few times. Now let's remind ourselves that the normal value in this section, and let me highlight it just for fun, the normal value is going to be smaller than our weight value. And the reason why is because we actually have a force applied in the y value. So, and actually I take back, now we're just going to write on this page for simplicity's sake. So let's clear ourselves a little spot. Let's make sure we have the highlighter turned off, turn the pen back on. Let's write some stuff right here. That normal value is going to be equal to the weight minus the force in the y direction, because normally the normal force and the weight would be equal to one another, but because we have this y component for the force applied, we're going to subtract that out. And what we see is we're going to have 196 minus 26.05. Now you might be saying, wait a second, where'd you get 196? Well, I think I did some sneaky math when you weren't looking, and I found the weight. Yeah, I totally did that. I found the weight. Remember that weight is equal to mass times gravity. So weight is equal to 20 kilograms multiplied by 9.8. That means that weight is equal to 196. Oh, that sneaky math. So anywho, back to our normal. What we see is that our normal value is going to be 196 minus 26.02. We find that our normal value then is going to be 169.95. Let's just round that up to 170 newtons for our normal value. And that's why this arrow for our normal value, so that's why this arrow is slightly smaller than this arrow down here, because there's more components that are going to be influencing that force in the y direction. All right. All right, next let's talk about our force in the x direction. We have motion in the x direction. We know that we are going to be using this equation right here to find our force in the x direction and find really our sum of our forces in the x direction so that we eventually can find our F equals ma and find our acceleration. So now let's jump to a new slide for simplicity's sake. We're going to have to write down a few things. Let's remind ourselves. Let's get a pen. Let's write in a funner color. Our F in the X is equal to our force applied, which in this case is our tension, minus our force of friction in the K because it's kinetic. All right, so now that we see that, and that K looks bad, all right, now that we see this, we have to change one quick thing. We're not talking about tension here. We're actually going to be talking about the force applied in the x component. So you can write that as Tx or F applied x. We don't want to mix it up with our f of x here. So really, if you want to write it as Tx or F applied x, really the choice is yours. It doesn't matter. They're both going to result in the same thing and give us the same result. It's not something to get hung up on. I know some of us get a little nervous about changing the notations of our variables. Don't get hung up on that. Make sure you understand the concepts. What we're talking about in this concept, we're going to jump back quick. What we're talking about now for the total forces in the x component is going to be the force applied in the x and also the force of friction. So those are the two forces we're talking about right now. The force applied in the x and the force of friction. Let's highlight them just for fun. I like that highlighter. So for the force applied in the x and the force of friction. So now let's jump back and actually do some math. We found on our previous slide, found on our previous slide, oh, that's a terrible color. Found on our previous slide that the tension in the x value was 147.7 newtons. And we found our force of friction to be, did we calculate that yet, or am I just pretending we calculated that? Let me check. We'll find our force of friction to be a value that we still haven't calculated. Now, a reminder from about the second slide that the force in the kinetic, force of friction for the kinetic value is going to be equal to the coefficient of friction multiplied by the normal. Well, remember, the normal was different here. The normal was not equal to the weight. So for our force of friction, we are going to see, what was our kinetic value? 0.14. That's from the beginning of the problem, multiplied by our normal force, which we calculated to be about 170. That means our force of friction is going to be equal to 23.8 newtons. Splendid. So now we can jump back over here, and we can actually plug that into our question, 23.8 newtons. So our sum of our forces in the x component are going to then be equal to 123.9 newtons. Awesome. Now we can use this to find our acceleration value. Because remember, F equals ma here, and really the sum of all the forces in the x value will give us our acceleration in the x value. And the mass of the object is not going to change based on whether we're talking about x or y components. So let's do a tiny bit more plugging and chugging. We see that 123.9 is equal to the mass, which was a given value to be 20 kilograms multiplied by a and the x. Divide by 20 on both sides, and we find that our acceleration value in the x component is equal to 6.2 meters per second squared. All right, so this is what we're going to do because that was 30 minutes of awesomeness in physics. What I'd like to do is I would like to stop this video right now, give this to Miss Hellenbrand, and make sure that you have a chance to see this on the YouTube page. I'm then going to make another video for Atwood machines, tabletop questions, and ramp questions. Hopefully this will not only give your brain a break, but this will also make sure that this video for sure gets up on the computer before the end of the day and give you a chance to watch it.